Hello everyone. Today we are going to discuss the concept of torque. We use Greek letter tau to represent torque, and torque is a vector quantity. So we use this symbol to represent torque. The tendency of force to rotate an object about an axis is measured by a vector quantity called torque. So I am writing the tendency of a force to rotate an object about an axis. Okay. We are going to discuss the concept of torque. Torque is represented or is denoted by the Greek letter tau, and torque is a vector quantity. So we use this symbol to represent torque. The tendency of force to rotate object about an axis is measured by a vector quantity called torque. So I'm writing the tendency of force to rotate an object about an axis is measured by a vector quantity called torque. Okay, so we need to understand this. And torque is similar or is equivalent to force in linear or translational motion. It is impossible, okay, to exert torque without exerting a force, and torque depends on force and point where the force is applied. Okay, torque can change the rotational motion of object either by making it to rotate faster or slower. So these are the points to be noted while discussing the concept of torque. Now, let us consider a range which is pivoted about an axis passing through O, and we can take O as the origin. Okay, so let the force F, okay, is acting from this point, and we know torque depends on force and the point where the force is applied. So force is acting from this point, clear? And this, okay, distance is the position vector, clear? So we are taking O as the origin. So this length is the position vector. So vector R, okay, this is the position vector, and let us produce, okay, the position vector in outward direction, okay. So we have this, and let this angle be theta. So we have this. So with reference to figure 1, okay, with reference to figure 1, the torque in magnitude, okay, tau, due to force, I'm writing in magnitude, F is tau equals R F sine theta, okay, and let us call it equation 1. So equation 1 gives the magnitude of torque and theta, okay, this is angle between position vector and force, okay. So we have this. Now let us associate, okay, sine theta with force, okay. Then from 1 we get, then from equation 1 we get torque tau equals R. So I'm keeping sine theta with force. So we have this. Now let us come to figure 1 once again. Now we can resolve this force, okay, resolve this force into two components. One parallel to the position vector R. So this is the parallel component of force. Next, perpendicular to R. So what we are doing, force F, okay, is resolved into two components, okay. So we have this one parallel component, okay, next perpendicular component. So we have this sorry, and we know the parallel component is F cos theta, okay, and the perpendicular component is F sin theta. So we can write this expression in this way: torque tau equals R, and we have perpendicular component, okay, R times the perpendicular component of the force. So let us call it equation 2, okay, and this is F sin theta, okay, and this is the perpendicular component of force, clear? Now I'm drawing or producing force F in backward direction, okay. So I'm producing force in backward direction. I can produce force in forward direction also, okay. So this is a line, okay. So we can see the dotted line dotted line, okay, they are collinear with force, and we can draw dotted line, okay, we can draw on both sides of force, and we can extend, okay, we can extend these lines up to infinity. So these lines are called line of action of force. Clear? And so let me write, this is called line of action of force. Now let us draw perpendicular from point O to the line of action of force. Let me erase this, okay. So this line is perpendicular to the line of action of the force, and as I said earlier, okay, this, okay, this distance or length is the position vector. So we need to note this, and this angle is theta. So we have this. Now let us take force acting from this point along this direction, and let this angle be theta, okay. Now let us draw line of action, okay, on this side of the force. So as I said earlier, we can draw line of action on both sides of the force, and line of action, okay, is collinear with the force, and it extends up to infinity. Now what we do, we resolve this force into two components. One, F parallel, okay, this is F cos theta. Next, F perpendicular, okay. So we have perpendicular component of the force. So this is F sine theta, and let us draw perpendicular, okay. Let us draw perpendicular from point O to the line of action of force. So this is line of action, okay, of force. Now in this triangle, or in this triangle, we can find sine theta, okay, and sine theta equals, we know, sine equals perpendicular by hypotenuse. So perpendicular is R perpendicular, and hypotenuse, okay, this distance. So this is position vector. So in magnitude we can write in this way, okay, R. So as I said earlier, this distance is the position vector. So in magnitude we can write in this way. Clear? So this distance is R in magnitude, okay. This is R in magnitude. So we can write sine theta equals R perpendicular by magnitude of position vector. Clear? So we have this. So we can write R perpendicular equals R sine theta. So we have this. Clear? We have this. So from this triangle or from this triangle, we can find R perpendicular equals R sine theta. Now, Now, let us associate sine theta with r, okay? Then from equation 1, we can write torque tau equals, I'm keeping r sine theta within the bracket, and we have F. So torque tau equals, and we know r sine theta is r perpendicular, okay, and we have F. So we can define torque in two ways, okay? So torque tau equals r times the perpendicular component of force. Next, torque tau equals r perpendicular times the force. Clear? And this, okay, r perpendicular, which is r sine theta, is called moment arm or is called lever arm. Okay, so if we generalize this expression, then we can write torque tau equals force times, okay, the perpendicular distance. Okay, so we can also understand torque, okay, in this way. Now, the unit of torque, okay, the unit of torque is Newton meter. So this is to be noted, okay. So Newton meter is the unit of torque. Now, let us come to this figure once again, okay. So what we find, torque, okay, tau equals, so when we take this expression, okay, this equals r times F perpendicular. So we have this, and we know F perpendicular is F sine theta. So what we find is that, okay, we find the parallel component, okay, that is F cos theta is parallel to position vector, okay, and F cos theta, okay, or this is the parallel component, okay. So let me write in this way. This is the parallel component of the force do not cause rotation, okay, about the pivot. We need to understand why the parallel component do not cause rotation. It do not cause rotation because its line of action, okay, line of action is parallel to the axis or position vector. We can see f cos theta, okay, its line of action is parallel to the axis, okay, its line of action is parallel to the axis or is parallel to the position vector. And we find f sine theta, okay, which is the perpendicular component, okay, is perpendicular to the position vector or is perpendicular to the axis, okay, this is perpendicular to the position vector or the axis. So therefore we can draw conclusion that only f sine theta, okay, causes the rotation about the pivot or axis. Therefore we can write torque tau equals r times the perpendicular component of the force, or we can write in this way, torque tau equals r times f sine theta, okay. So we can write in this way, so we have this. Now in this expression, okay, in this expression r, okay, represent the shortest distance between the axis, okay, between the axis. So you can see axis is passing through this point, between the axis of rotation and the point of application of the force. Force is acting from this point, and the point of application of force. So we have this. Now let us discuss the sign convention of torque, okay. So I'm erasing this. So sign convention, okay. So we can have, or we can write torque tau equals plus minus r times f perpendicular, okay. So I'm taking this. Now if the perpendicular component, okay, this perpendicular component of the force, okay, tends to, or if it causes, tends to rotate in counterclockwise, okay, that is anti-clockwise direction, okay, then tau is positive. We take tau as positive, okay. Next, if The perpendicular component of the force tends to or causes, okay, rotate in clockwise direction, then torque is taken negative. So these are the sign convention we take while discussing the torque.